Okay. Wow. We're at the last one. So this is ethers. Trying to see the reactions, right? Now we do the preparation. First, we're going to do for preparation, we're only going to do two methods. Okay. The third one would be for if you want to make aryl ethers, which is an ether on a benzene ring. So this first one is going to be called Williamson synthesis. Okay, we are going to do two for the basic ethers. So the first one is going to be called Williamson synthesis. Okay, it was made by this guy called Williamson long back, I think in 1978 or something like that. So basically what he did is, what we know as an ether, we know that an ether you have an oxygen between two carbons. Okay, you have your R, then O, then R, like this. This is an ether. So we want to have this situation. So what we are going to do is we are going to use an alcohol, which is an OH. Then we're going to remove the H. We start with an alcohol, we remove the H, then we put the R. So what we're going to do in Williamson, it's a two-step process. The first step is we do what we know alcohols do, is we know they react with metals, right? So what we're going to do is we react an alcohol, primary alcohol. We like primary alcohols. Secondary alcohols may work, but tertiary alcohols definitely will not work here. If you have, say, something like R, which is bonded to an R and an R and an R, and then your OH, these will not work in the Williamson synthesis. Okay, here is this is the most basic one. So if we have then an ROH, if this guy reacts, okay, to this is your alcohol, if it reacts with sodium, so we will also use 2 moles of sodium, then what we are going to get is we are going to get 2 moles of this guy, RO minus, then Na plus. Okay, RO minus Na plus. This is called your salt, if you remember that. So acid plus salt, because your alcohol, we said, behaves like an acid. Acid plus salt gives you acid plus metal gives you salt plus hydrogen. So you get hydrogen be removed and you have sodium. The reason why we are doing 2 moles is so that we get H2, because hydrogen always exists in diatomic form. Then we are done. So that's going to be the first step. The first step is you convert. What do? You convert alcohol to an alkoxide. Remember, we said it's called an alkoxide. This something with a negative oxygen is called an alkoxide. There we go. It's a metal alkoxide. So you can say convert alcohol to metal alkoxide. Okay, metal alkoxide. Then the next thing in Williamson synthesis, that's step 1. This is step 1. Step 2 now. In step 2, what you're just going to do is you're going to react the alkoxide with a haloalkane. So I'm going to take this, my alkoxide, RO minus Na plus. This reacts with a haloalkane, which is an R and an X. Okay, and what you're going to get now is this Na takes the X and go away, and they go away together. So I'll get RO, R prime. Let's call this R prime. So it's now R prime with an X. So now this RO meets the R prime, and then we have the NaX leaving. So here we said in step 2, what happens is reaction between, let's say, what should I say? I'll say alkoxide here. Alkoxide displaces halogen. Okay, displaces halogen in halide, in alkyl halide or haloalkane, in haloalkane. Haloalkane is also called alkyl halide. Okay, in alkyl halide. So here we can say haloalkane. So what we're saying is this RO minus is going to remove this X. Okay, the halogen, and they're going to be together. That's going to be your 2. That's your Williamson synthesis. You just take an alcohol, primary alcohol, react it with a metal, you get a salt. Then you take that salt, react it with a haloalkane, then you get your ether. That is going to be your Williamson synthesis. The other way, so way number 2 of preparing it is what we call the alcohol. We call it the alcohol sulfuric acid method. Sulfuric acid method. We use an alcohol again to make our ether. So we are going to use an alcohol again. And what are we going to have? We have an alcohol, and we just react it with the same conditions that we did in dehydration. So it's like we have an alcohol, CH3, then H2, then OH. Remember, for dehydration, we used 443 kelvins and 300 atmospheres. But in here, we'll just put the acid, H2SO4. And this is the dehydration. So dehydration, it will lead us to an alkene where the O goes in 1. Remember, in dehydration, for alcohols, remember that we had two different things. In dehydration, O would go and H would go on the next. So we would have a CH2, okay? We have a CH2. Remember, this was, oh my gosh, what did I put here? I wanted to say CH2, CH3, then CH2, then OH. So here it now becomes a CH2, then here it becomes a CH. So it's like instead of having a CH2OH, it becomes a CH2 here from a CH3. Then this becomes a CH2 and the OH is gone. So we take OH and then H from the next one in dehydration. Remember that for alcohols, in dehydration, we took OH from one, H from the other. Okay? Now, what are we going to do here? We are going to have a slightly different reaction. 413, that's the one we want. 413 kelvins with the same stuff, okay? Just a little lower temperature, 30 degrees lower, 413 kelvins. You will now get a diethyl, okay? Diethyl ether. Let me show you. You have something like this. C2H5 and then O, then C2H5. So this same thing that we had, the only thing now is, you see here, CH3CH2, we remove the OH only, and we have the O now, and we have another CH3CH2, okay? So that's what we do. We convert two CH3s, so that's what we call a C2H5. It's a CH3CH2. Now, this makes what we call a symmetric ether. So, symmetric ether. If you want to make a symmetric ether, you use this. What do? You take an alcohol, you react it to sulfuric acid at 413 kelvins, then you get a diether. Okay, it's called a diether. So this one, what is on this side is ethyl, then here again is ethyl. So that's why we called it a diethyl ether. Okay, diethyl ether, diethyl. Then we can now just say ether because we've already put ether. So it has two ethers. It says symmetric. That means the left side is the same as the right of your oxygen, right? That's what happens if you take an alcohol and react it with sulfuric acid. And we are done. These are the two ways to make ethers. Now, the last thing which you want to know is the preparation of aryl ethers now. Aryl ethers, okay, which means an ether on a benzene ring. Aryl ether, what do? We just take a benzene ring like this. Here is our benzene ring, okay? Here is our benzene ring. And this guy will have, it's an alcohol, so it will be a phenol because we always start with an alcohol when we're making this thing. Then we are going to add NaOH. And what it's going to do is it's going to lead us to something very nice. Look at it. When we add NaOH, what do we have? We are going to have this guy react with him here. So what do we have? We're going to have a salt first. That's the first thing we're going to have. It's a salt. So again, this becomes O minus Na plus, okay? And then remember, we'll release H2O. Then we are going to react that with our second step, which is similar to what we did in the very first method. Very first method, we reacted with Na, but for phenol, we make it an NaOH. Second step, we now react with our halide, or alkyl halide, haloalkane. And what's going to happen is we will just have, so call this R prime, we'll just have this thing, this thing, same, if we say, make it like this, here, skip there. So it's going to be now O, then R prime, okay? It continues. We can just call it R since there was no other R, so we can just call it R. And this is what just happens. The R now fits in. So first we react with NaOH, we get this alkoxide, and then we react with our metal. Similar to the first one, but only that in the first we use sodium itself. In here we use sodium hydroxide. And these are the ways to make an ether. Now you see just one reaction of ethers because they're not reactive and you are done.